So now we're going to find the correct orbitals for a molecule starting from a linear combination of the atomic orbitals. To do this, note that if we actually had the correct wave function, the Schrödinger equation tells us that the Hamiltonian operating on the wave function returns the correct ground state energy times the wave function. So multiplying this equation by the left by psi star using the Dirac notation and integrating, so in Dirac notation then we can solve for E. Now this is strictly a correct expression, but not very useful at this point. Now suppose we use an approximate expression for the correct ground state wave function where the Fi's are atomic orbitals, and we're going to add up as many as we need to get a correct description of the molecular orbital. Now, if we plug these into this expression here, one can show that the terms that come from adding some departure from the correct wave function add additional energy to this expression for the energy, and therefore the energy that you calculate with the wrong wave function is always higher than the energy that you get by solving the Schrödinger equation for the correct wave function. Therefore, if we adjust our linear combination of atomic orbitals so as to give the lowest possible energy, we will come as close as possible to the correct molecular orbital. Now, in order to make this a little tidier, I'm going to introduce some definitions. I'm going to say that Hij is shorthand for an integral of this sort. And an overlap element of this form, Sij, is Fi Fj. We're also going to use the fact that Hij, and the same applies to the S's, is Hji. This is actually a general property of functions that solve an eigenvalue equation. For these equations to be physical, the operator has to have this property. It's called being a Hermitian operator. In Chapter 2, we exploited the symmetry of the property to introduce this definition. So we can now go back to this expression for energy, and we can substitute our linear combination of atomic orbitals and these definitions. Let's do that. So to keep things simple, we're just going to illustrate the case of an expansion of the molecular orbital in terms of two atomic orbitals. So we'll now place these into our expression for E. And then we will multiply out all the appropriate terms. So we'll operate with H on F1, F2, pull out the C's, and use the definitions we just introduced. When we do that then, let's just take an example here. Let's operate with H on F1, and then from the left with F1, and we will end up then with a term C1 squared H11. Now we will do the same between F1 and F2, and so we will end up with two terms now. Remember, H11 equals H12, 2C1, C2, H12, and then finally we have C2 squared H22. And then similarly on the bottom of this expression, we have C1 squared S11 plus 2 C1 C2 S12. Remember, S12 equals S21 plus C2 squared S22. Now, how do we go about choosing the best combination of these constants C1 and C2? The answer is we choose values that will minimize the value of E, i.e. dE by dC1 or C2 is 0. We can take this derivative easily by multiplying both sides of this expression here by the denominator, and then taking the derivative and setting it equal to 0. Now, a simple way to do this is to take the chain rule. So we take the derivative of this times E with respect to C1. So we have C1 squared here, and the last term has a derivative that is 0. Now we have a term in dE, dC1, times this whole parenthesis again, but this is equal to 0. And then this whole thing is in turn equal to the derivative of the right-hand side with respect to C1. So 2C1 H11 plus 2C2 H12. So now we have a linear algebraic expression in E, C1, C2, and these matrix elements that we have defined, S11, S12, H11, and H12. Rewriting the algebraic equation that we just derived, we obtain the following expression. Note this is exactly similar to what we derived in Chapter 2 if we were to set this S11 equal to 1 and this S12 equal to 0. If we repeat the process and take the derivative with respect to C2, we end up with a second linear equation. So we have two equations and two unknowns which we can now solve for C1 and C2. In order to have non-trivial solutions, we require that the secular determinant, which is the product of this term with this term, minus the product of this term with this term, be equal to 0. This gives us a quadratic equation which we can solve for two values of E, the larger value corresponding to the antibonding state and the lower value corresponding to the bonding state. We can then put these values for E back into this system of two linear coupled equations and solve for the two values of C1 and C2. One can generalize this in a straightforward way to many states. In general, if one uses a basis of n states, one will have an n by n secular determinant, which one will then solve for an nth order polynomial, and one will have n different solutions for the E, which one can substitute back into the linear coupled equations, finding the values of coefficients for each particular value of E. You can see this mathematical machinery put to use in section 8.4 of the book, which does a more thorough treatment of the hydrogen molecular ion. In particular, we include in our Hamiltonian now proton-proton repulsion as well as proton-electron attraction, so we can get out the full potential, something we didn't do in Chapter 2, and the effects of the overlap between the states, SAB. In that section, we introduced the notation that the molecular orbital for the bonding state is called the sigma orbital, sigma 1s because it comes from the 1s atomic states, and the sigma 1s star state refers to the anti-bonding orbitals. Here is a similar notation applied to the states of the lithium diatomic molecule made from two lithium atoms. Each lithium atom has 3 electrons in s states, and so we therefore now have molecular orbitals filled up with 6 electrons on the molecule. The states that come from the 1s atomic states, the sigma 1s and the sigma star 1s, each contain 2 electrons and overall do not contribute any energy to the bonding. However, the sigma 2s states can take the remaining 2 electrons into the bonding orbital, and it is this lowering of energy that comprises the bond that holds a lithium diatomic molecule together.